Calculus 3 video lecture number 20 on double integrals over general regions. So suppose we need to evaluate a double integral, and this time our region of integration is not a rectangle, but some more general region, which we're going to refer to as D. Other textbooks may refer to it as R, same thing. So again, what we're going to do is look back at our old concepts and skills and extend them to fit these new situations. So let's think back how we would determine whether or not to integrate with respect to x or with respect to y when we were finding the area between two curves. So if we notice that we could write y as a function of x, and on some interval from a to b there was one function that was always on top of another one lying above it, then it made more sense, right, to create all of our rectangles moving in the x direction. The bases would be delta x. And then the height of each rectangle could be found by taking the difference in the function values. You would take the top function minus the bottom function to get the height of the rectangle. And in that case, we would integrate with respect to x. So to find the area between the curves, we would set up an integral from a to b with g sub 2 of x minus g sub 1 of x dx. All right, now other times, if we had x expressed as a function of y and we had one curve always on the right and another always on the left, it made more sense to stack our rectangles moving in the y direction. And in that case, the base of each rectangle would be a delta y, which becomes dy. And then the height you could take by you could find it by taking the values of the curve on the right and subtracting the values on the left, right minus left. So you would have integral from c to d, right? You would have to match limits for y direction this time of h sub 2 of y minus h sub 1 of y dy. Okay? So now what we're going to be asked to do is integrate some function f of xy over this region. So just like before in the previous lesson, we had a rectangular region and we would imagine that as the base of our solid, right? In this case, now we have this region D and that's the base of our solid. So we have these function values, z values, floating either above or below D. And now we want to integrate it over this region. So we have to either set them up as dx dy or dy dx, depending on really the configuration of D and what makes more sense for the problem. Okay, so here are going to be your two options. Always remember the outer limits must be the constant ones. So if I have a to b on the outside, then I'm going to have g sub 1 of x, g sub 2 of x, and then f of xy dy dx. And that should make sense because if we're integrating with respect to y, these are my limits for y. And then after we get that value, lastly, I have to integrate with respect to x, and these are the limits for x. You have to have the constants on the outside. Don't put function values as your outer limits. And then the other option would be to go from c to d last, and then inside you would have h sub 1 of y, h sub 2 of y. So notice the upper limit's going to be the function on, or the curve on the right, lower limit's a curve on the left, and then we have f of xy dx dy. So notice everything's matchy-matchy. These match for y, those limits, and these are limits for x. Okay? Every single time you do these problems, sketch the region D, the base region that you're integrating over. Even if you're not asked to explicitly in the problem, if you don't, most likely things will not work out. Okay. So here we go. We've got a double integral over D. I'm not going to pay attention to f of xy until later. I'm going to focus on integrating it once I get everything set up and good to go. So right now, I'm going to look at D here. D is the region where x is bounded between 1 and 2, and y is bounded between 0 and 2x. All right, so I'm just going to draw that region in the xy plane. This looks so messy. Let's clean it up. Okay, xy plane time. Here we go. Now, x is between 1 and 2, so we're just going to stay in the first quadrant. And then y is between 0 and 2x, so y is going to have to go up to 4. No problem. So if y is 2x, at 1, y is 2, and at 2, y is 4. So here's y equals 2x. And then x is bounded between 1 and 2. All right, from here to here. So here's our region D, over which we need to integrate. All right, so you have to think, does it make more sense to integrate with respect to x or y first? Well, in this case, I'm noticing it's easier to set it up to integrate with respect to x last, right? And use these constants as my, excuse me, outer limits of integration, because I basically always have y equals 2x on the top and y equals 0 on the bottom. So this will be the top curve, y equals 2x, and then y equals 0 is the one on the bottom. So let's go ahead and set it up. I'm going to have the integral from, remember, constant limits go on the outside, so 1 to 2, and then I'm going to have 0 to 2x, and then f of xy, which is 4y over x cubed plus 2. Now dA is going to need to be dy dx. Remember, double check that you did it correctly. So 1 to 2 refer to limits in x, so those are going to go on the outside. 0 to 2x represent the bounds on y, right? Look at y. Y lives between 0 and 2x, so those are the bounds on y. All right, let's go ahead and anti-differentiate this guy. So I'm treating all my x's as constant. So you're just thinking of taking the antiderivative of 4y with respect to y. So it's going to become 4y squared divided by 2, which is 2y squared. So I'm going to leave this 1 to 2 out here. Now I have 2y squared. I'll just put it over this x cubed plus 2. That's just a constant. And now I'm going to evaluate it from 0 to 2x, and then I still have that dx. Okay, now be careful. The limits of integration only get substituted in for y, right? Because I'm treating x as constant. So I have integral from 1 to 2. And then this is going to be, now if I substitute in a 2x for y, I'm going to get 4x squared. Times 2 is going to be an 8x squared over x cubed plus 2 minus, and then if I substitute in 0, I'm just going to get 0 for the whole term, dx. Okay, looks good. So then now I have integral from 1 to 2, 8x squared over x cubed plus 2 dx. And then we're going to do a u sub. How do I know that? Because I have x cubed plus 2 in the denominator, and I notice in the numerator I have 1 degree lower, right? So I'm going to let u equal x cubed plus 2. Then du is going to be 3x squared dx. So that means 1/3 du is x squared dx. All right. So let's go ahead, and then we can change our limits of integration as well. So if u is equal to x cubed plus 2, u of 2, the upper limit, is going to be 2 cubed plus 2 is 10. And then u of 1 is going to be 1 cubed plus 2, that's 3. So then now my integral becomes, let's pull that 8/3 outside. I'm going to have integral from 3 to 10 of 1 over u du. So this is going to be 8/3 natural log absolute value of u evaluated from 3 to 10, which I could write as 8/3 natural log of 10 minus natural log of 3. And of course, the finishing touch, you write that as 8/3 ln 10/3, right? Nicely done. Let's box it with pride. Okay, a couple things I want to point out. Make sure you put the absolute value around u or your variable expression. You can't drop them until you've actually plugged in your limits of integration and made it non-negative. Otherwise, you're going to have problems. Okay, Good, let's try another. This time the question might be a little peculiar to you. It says use a double integral to find the area bounded by y equals negative x squared and x plus y equals negative 6. Now typically you probably think of double integrals being used to find volume, but I did mention in the previous lesson it can be used to find an area for a very special case. If you just integrate the function who's equal to 1 all the time, right? So if I take the double integral of just dA, I get back area. If you need to review the little discussion in the previous video, that's fine. So let's go ahead, and to start off the problem, I want to know where these two curves intersect. So I've got this parabola opening downward and a line, right? So let's get their intersection. So we're going to have x. I'm going to substitute in for y negative x squared. Sound good? So x minus x squared equals negative 6. I'll set everything to 0. So 0 equals x squared minus x minus 6. And lo and behold, it factors. So x minus 3 times x plus 2. So we get x equals 3 and x equals negative 2. All right, well, I want the actual coordinates of intersection, so the y values I can get by plugging into either equation. I like negative x squared, it's just more straightforward. So that means these two curves intersect at 3, negative 9, and negative 2, negative 4. All right, so let's draw our graph. It looks like most of the action's happening in quadrants 3 and 4, so I'm really not going to draw too many positive y values here. So let's put the x-axis way up here at the top. But be sure to draw it straight, you know, much better. Okay, here's the x-axis. I'm going to have to go all the way to positive 3, all the way over there. 1, 2, let's just do negative 3 for good measure. And then down to negative 9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. So negative x squared, that's no big deal to graph. And then let's make sure it's going to intersect the line nicely. So we have 3, negative 9. And then we also have negative 2, negative 4 as another point of intersection here. And then looking back, I can tell that the y-intercept of this line is going to be negative 6. So let's just add that in for good measure. Okay, so that's x plus y equals negative 6. And then now I'm going to graph the parabola. So it's just vertex sitting at the origin, opening downward. And it's going to intersect right there at negative 2, negative 4. Nothing happens over here at 2, 4, but let's just, at 2, negative 4, but I'll just add it in for symmetry purposes. And then there's the other intersection at 3, negative 9. Okay, very nice. So remember, this is y equals negative x squared, and then the line is x plus y equals negative 6. Okay, so let's see what is the region D that's bounded by these two curves. It's right here. So would it make more sense to stack rectangles moving in the x or the y direction? Well, it makes more sense if we integrate with respect to x. Don't you agree? Because negative x squared is always on top, and then the linear function is always on the bottom. So it looks like we're going to integrate with respect to x last. Those are going to be our constant limits, and we're going to integrate with respect to y first. Okay? The only thing is I have to make sure I can write both of them in terms of x, both equations. So I'm going to rewrite this as y equals negative x minus 6. So I can use it for my lower limit. Okay? So on the very, very outside go your constant limits of integration. Those are going to be for x. So those are going to go from negative 2 up until positive 3. Then the next limits of integration need to represent the bounds on y. Okay, so what curve's bounding the region below? It's negative x minus 6. What curve is bounding the region above? It's negative x squared. And then remember, I don't have a function, it's just 1 dy dx, because I want this double integral to represent area. Okay, So now we're going to go ahead, anti-differentiate with respect to y. Well, since I just basically have a 1, antiderivative is going to be y. So we have negative 2 to 3, y being evaluated from negative x minus 6 to negative x squared dx. And then I'm going to evaluate it at the upper and lower limit. So I'm going to have negative x squared minus negative x minus 6 dx. And now it's like we got in a time machine and we're back in our Calculus 1 class, and you were told, oh, when you want to find the area bounded between two curves, you do top minus bottom, right? If you're going to integrate with respect to x. Boom. Okay, and then from here, it's just pretty straightforward computation. So no need to bore you. You should end up with 125 over 6. All right. Fabulous. The setup is really the meat of the problem, wouldn't you agree? So let's look at another one here. So we have double integral over region D of x times sine of y dA. And this time they're telling me D is the region where y is bounded between 0 and pi halves, and then x is bounded between 0 and cosine of y. So we could graph it if we want, but it's pretty straightforward. If I imagine the graph of cosine, it's going to go from starting at 1, right, when you substitute in 0, down to 0 when I plug in pi halves for y. So it's not going to be too wild. Everything looks pretty straightforward. We can just go ahead and set it up. But if you're dead set on graphing it, why not? So in this case, we have x is equal to cosine of y, and y is bounded between 0 and pi halves. So here's x, here's y. Y is bounded between 0 and pi halves, and x is equal to cosine of y. Okay, so when y is equal to 0, cosine is going to be equal to 1. And then if we move along where y is equal to pi halves, then cosine is equal to 0. So we have something like that. That's our region D. Okay, so constant limit goes on the outside, so 0 to pi halves. And then on the inside is going to go 0 to cosine of y. And then we have x times sine y. Now be careful. These limits refer to y, so dy has to be on the outside. So I have dx first and then dy. Very nice. Okay, so I'm treating sine of y as a constant. I'm going to anti-differentiate with respect to x, so I'm going to get 1/2 x squared. And I really recommend, like, that 1/2, just put it all the way outside the integral so it doesn't bother you or get in the way. So 1/2 is going to go here. 0 to pi halves, I'm going to have now sine of y, that's a constant, times x squared, evaluated from 0 to cosine of y dy. And then let's go ahead and evaluate this at the upper and lower limits. Now remember, I'm substituting in the limits just for x. So I have 1/2 integral from 0 to pi halves sine of y times cosine squared y minus basically 0 dy. Okay, so what do? I have cosine squared times a sine y. Well, this is a beautiful time for a nice u sub, right? I want to let u equal cosine of y. Why did I pick it to be cosine and not sine? Because whichever one is the odd man out, that you only have one little guy hanging out there, that needs to be your du. So it gets all absorbed in the substitution. So whichever one has the higher exponent, don't throw it in for u. So du is going to be negative sine y dy. Okay, can you just do this in your head now so we don't have to change all the limits and all that hoop-de-loo? So think about it. If cosine is u and I anti-differentiate, it's going to be raised to 1 higher power, so 1 power higher powers. So we're going to have cubed divided by 3, right? U cubed over 3, but u was cosine, so there we go. And then just slap a negative on there from this guy, and then we're ready to roll. So I've got negative 1/2 times that 1/3 times cosine cubed y from 0 to pi halves. All right, then you don't have to go through changing your limits and all of this and that. And then from here, we're going to have a negative 1/6. All right, cosine of pi over 2 cubed minus cosine of 0 cubed. Well, cosine of pi over 2, that's just 0. And then cosine of 0 is 1. So I have negative 1/6 times a negative 1, which is positive 1/6. All right. Very good. Let's consider another example. Okay, so next example has us evaluating the double integral of y times e to the x dA, where d is the region given by the triangle, whose vertices are at 0, 0, 2, 4, and 6, 0. Oh, look at them making us do all the work and come up with the equations for the region as well this time. Okay, that's fine. So here's x, here's y. Let's graph this triangle. There's 6, 1, 2, 3, 4. And let's put those vertices on there. So we've got 0, 0, 2, 4, 6, 0. Okay, so here's our region. Now you tell me, does it make more sense if you were to try to, just pretend you're in Calculus 1 when you think about this part. Does it make more sense to try to find the area in here if I were to integrate with respect to x or with respect to y? So do you always see one curve on the bottom or one function on the bottom and one on the top, or do you always see one on the right and one on the left? I always see one on the right and one on the left, yes? So we have this line here on the right, and then this line over here on the left bounding the region, and then we can get the equations pretty easily. If I were to try to do top and bottom, you could do it, top minus bottom, but then you would have to split it into two, right? Because you would have, this is region 1, this is region 2. Since where x is equal to 2, it switches which equation is bounding the region D on the top. All right. It doesn't matter which way you do it, it's just going to be more work, right? If you do it the second way, because then you're going to have two integrals to contend with. So let's see, what are these lines here bounding the region? So this is at 2, 4, correct? So that means the slope is 2, y-intercept is 0, so this is y equals 2x. And then on the other side, if that's at 2, 4, this is 6, 0, so the slope is negative 1, and I can tell the intercepts are going to be 6. So that's x plus y equals 6. But remember, if I'm going to be integrating here using right minus left, I want to have my limits of integration with respect to y on the very outside. So I have to write x as a function of y. So this is going to be x equals 6 minus y. And then similarly here, I'm going to write it as x equals y divided by 2. Okay? So now let's set up our integral. So remember, constant limits have to go on the outside. So the region D is bounded in the y direction from 0 to 4. And then it's bounded in the x direction on the right, which is going to be the upper limit, the larger limit, is 6 minus y. And then it's bounded on the left, the lower limit, by y divided by 2. And then now you plop in your function, f of x, y, so y times e to the x, dx, and then dy. Okay, are you with me? Fantastic. So now let's go ahead and anti-differentiate with respect to x, right? You're just going to treat y as a constant, pay him no heed. So we have 0 to 4 hanging out there. And then now antiderivative of e to the x is e to the x. We love it. So y times e to the x. Limits are from y over 2 to 6 minus y. And then you still have that dy. Okay, and then don't forget, these limits get plugged in only to x, because that's what we anti-differentiated with respect to. So we're going to have integral from 0 to 4 of y times e to the 6 minus y minus e to the y over 2 dy. And then perhaps you stare at it now and you go, no, it can't be. Something must have gone wrong, because this looks like a rather intimidating problem that requires integration by parts. But you are correct. That's exactly what we need to do. So here we go. Do not distribute the y, because then you're going to need to set up 2 integration by part problems. We can handle it all at once by letting this entire beast right here be dv. Okay, it's just going to be cleaner. Trust me on this one. So I'm going to let u equal y. So this is by parts time. Oh yes, we have to remember everything. So u is equal to y. dv is going to be e to the 6 minus y minus e to the y over 2 dy. Okay, and you're going to love it. Watch, it's going to knock out the whole thing. So then du is equal to dy, yes, and v is going to be negative e to the 6 minus y minus 2e to the y over 2. Okay, beautiful. So then from here, let's go ahead. Remember, you take this product here, which is going to be, let's distribute while we're at it, right? Okay, we can handle it. So we'll have negative y e to the 6 minus y minus 2y e to the y over 2, and then I have to evaluate that from 0 to 4. And then I subtract this product here, v du, but if I'm subtracting it and they're both negative, now it's going to become positive, and then I'm going to have integral from 0 to 4 e to the 6 minus y, don't mess with the exponents, plus 2e to the y divided by 2 dy. Okay? All right, really focus when you do this, because one little thing will just make the whole thing fall apart. Good, good, good. Now let's go ahead. You know what I'm going to do? I'm not going to evaluate these first 2 terms at the limits of integration just yet. I'm going to do that all at the same step, so it looks all nice and neat. I'm just going to anti-differentiate the second part first. Okay? So I'm going to rewrite this. I have negative y e to the 6 minus y minus 2y e to the y divided by 2. And then now let's go ahead and anti-differentiate these 2 terms. So antiderivative e to the 6 minus y, I'm just going to pick up a negative, right? So negative e to the 6 minus y. And then now I'm going to have to multiply by another 2. So this is going to be 4e to the y divided by 2. And then now all of this is evaluated from 0 to 4. You see how nice and neat that is because I waited to evaluate it? So this is a good tip even when you're doing limits too. Wait to do the same step at the same point in your computation. Okay, don't evaluate limits at different parts in the problem. Okay, here we go. Let's plug in 4 now for y. Well, that's the only variable we have left anyhow. So we have negative 4e to the 6 minus 4, so that's 2, minus, this is going to be 8e squared, minus e squared, plus 4e squared, so many e squareds, minus lower limit, let's put some parentheses here, lower limit's going to be 0, minus 0, minus, ooh, this is going to be e to the 6th, and then plus a 4. All right, so let's see here what's going on. These will cancel out. I also have negative 9e squared. And then this is going to be a positive e to the 6th and a negative 4. So I'll put it in descending powers. So I'm left with positive e to the 6th minus 9e squared minus 4. Wow, wow, wow. Okay, good job. That's that problem. Now I'm sure you might be curious, what if we were to set it up the other way and break up our region D into 2 parts, right? I did mention that was an option. So if you choose, you could break it up into 2 portions. I'll just draw this myself. So this would be integral 1, this would be integral 2, and you would have x last. Yes, I'll just zoom in. That way nothing else is in the way. So if you wanted to set it up as x limits with respect to x last or on the outside, okay, you would have to break it up from 0 to 2 and then from 2 to 6. So you would have integral from 0 to 2, and then you would do top minus bottom. So you would have 2x bounding it on top, 0 bounding it on the bottom, y e to the x, and this time dy dx, plus, and then your next integral, integral 2, would go from 2 to 6. Bounding it on the top would be x plus y equals 6, but I have to solve for y, so 6 minus x on the top, 0 on the bottom, y e to the x dy dx. And you would get the same answer. Isn't math so beautiful? So if you have some spare time and you want to confirm, why don't you verify that that would work as well? And you would have to still do by parts and all that stuff. So it's not like it's an easier computation. Okay. Moving on to the next example, find the volume of the solid under z equals 3x squared plus y squared. So that's our f of xy, right? Above the region bounded by y equals x and x equals y squared minus y. So I know this is a parabola, but it's opening up in the positive x direction. And then y equals x, we know what that is, right? That's a line. So let's go ahead and find their intersection. So y equals x, and we have x equals y squared minus y. It makes the most sense just to substitute in y for x, right? Into the parabola's equation. So we have y equals y squared minus y. So y squared minus 2y is 0. I can factor out a y. So they intersect at 0, 0 and 2, 2. All right, so let's draw this region. I mean, already, since I have x expressed in terms of y, I'm feeling like we're going to set it up with y last, right? With the limits for y on the outside. But let's just confirm. So they're going to intersect at 0 and 2, 2. Okay. 0, 0, 2, 2. This is y equals x. And then the parabola, y squared minus y, well, we could find the vertex. We know it's going to be when y is equal to positive 1/2. So it's going to be back here. Anyhow, it's also going to intersect, if y is 1, x is going to be 0. Just to throw a little more detail into this picture. Okay, so where's the region D? Can you see it? Or have you been lost now? No, it's right here. We got it. We're under control. Beautiful. So is it easier to bound the region by expressing it in terms of a curve on the right and the left, or on the top and the bottom? For sure on the right and the left, right? Y equals x is always on the right, and then on the left is good old x equals y squared minus y. So we're going to have our limits for y outside. All right, so the region is bounded in the y direction. Remember, these have to be constant from 0 to 2. And then in the x direction, the curve on the right that bounds it is y equals x. But remember, this has to be in terms of y. So we're just going to have y up here. And then the parabola is on the left, so y squared minus y. And then f of xy is right here, 3x squared plus y squared. And remember, the order is dx and then dy. Everything has to be matchy-matchy. 0 to 2 are limits for y, so that's on the outside. And then y squared minus y and y are limits for x. All right, and then this gives us 144 over 35. Nothing frightening happens in this computation, so we don't need to just sit here all day integrating polynomials. Good. Now let's move on to some more exciting sketching problems. Are you ready? So sketch the solid in the first octant bounded by y squared plus z squared equals 4, x equals 2y, x equals 0, and z equals 0, and then find the volume of the solid. All right, so let's imagine what's going on. So y squared plus z squared equals 4. Hopefully you remember this is a cylinder. Right, in the YZ plane, you're going to have a circle with radius 2, and then you project it parallel to the x-axis. X equals 2y, that's just a plane, as are x equals 0 and z equals 0. Okay, so let's graph what's going on first, and then once we have our solid, we'll figure out how to set up an integral to find its volume. So since I know part of it's bounded by a cylinder, which in the YZ plane is a circle of radius 2, I'll just go up to 2 in the z direction and 2 in the y direction. And then I'm going to project it parallel to the x-axis. Okay, and I notice here I have the plane x equals 2y also bounding the solid. So I'll stretch out x to 4. Since x is equal to 2y, that makes sense. And here we go. So we'll extend this portion parallel to the x-axis, extend this portion parallel as well, come down here and across. Let's fix that little bit up so it looks perfect. Good, good, good. And down here. So this point right here is 4, 2, 0. Okay, so I've got my cylinder going on. Now I have to cut the cylinder with the plane x equals 2y. So I think maybe the easiest way for you to imagine graphing it is just in the xy plane itself. This would be y equals 1/2 x, a line, and then you're going to project it parallel to the z-axis. So just look down at the xy plane as if nothing else is going on right now. You've got 0, 0, slope is 1/2, so it also goes through 4, 2, 0. And then this is going to be a plane now extending up and down in the z direction, and it's going to cut this solid here. So it's hard for me to draw it. Just imagine it's going to have this space here because this whole back portion, this whole portion is going to get lopped off. All right, good. Also, x equals 0 is bounding the region. So x equals 0, that's the YZ plane. Okay. So back here. And then z equals 0, so that's the xy plane is bounding it. So we've got this portion here, and then this like curved portion, which is getting cut by the plane x equals 2y. All right. Now let's think here. If we want to find the volume of this solid, I have to identify what the base region is to integrate over. And then the function that I'm going to integrate should represent the height in order to get its volume. Okay, so it looks like the base of this solid is a triangle in the xy plane, and the heights are determined by the cylinder in the z direction, right? So if I use the xy plane as the base, then z is going to give me the height. So let's solve for z. Let's get our function of x and y. So z squared equals 4 minus y squared, which means z is plus or minus, but since we're only in the first octant, I'm just going to choose the positive radical, 4 minus y squared. All right, now I need to draw out this base region in the xy plane separately so I can figure out how to set up the limits of integration correctly, the ordering and so forth. So in the xy plane, just the base, we've got that triangle going on, don't we? All right, now make sure you shade in the appropriate region. Otherwise, you're going to get the wrong volume. So here's x-axis, y-axis, 1, 2, 3, 4. Y-axis goes up to 2. And we know that we have 4, 2 is where they intersect. And did you catch that? Did you catch it, that the triangle is actually the upper half, not the lower half? I hope you did. Okay. So here, this is the equation, x equals 2y, or y equals 1/2 x, however you want to think about it. This is the base region. This is what we referred to as D in all of the previous examples. So would it make more sense to have our outer or last limits be y or x? Which is easier, to set it up as top minus bottom or right minus left? You know what? It's probably the same either way that you choose to do it. So let's go ahead, set it up both ways. Why not? We're so versatile. I'm going to set up with respect to x on the outside first though, okay? So if I have x on the outside, those are going to be the constant limits. So look at this region D, I'll call it D. It's bounded in the x direction from 0 to 4. So 4 bounds it on the right, 0 bounds it on the left. And then on the top, what's bounding this? Well, this equation here is y equals 2. And then it's bounded on the bottom by y equals x divided by 2. Yes, did you catch that? And then we have f of x, y, the heights, which are given by 4 minus y squared. And this would be a dy dx. Yes? Good. So that's one option. Or other option is I have limits for y last on the outside, so 0 to 2. So the region's bounded in the y direction from 0 to 2. In the x direction, it's bounded on the right by 2y, so that would be my upper limit. It's bounded on the left by x equals 0, and then you would have rad 4 minus y squared, this time dx dy. Okay, so look at us, so versatile. We've got two integrals set up. It really boils down to which one are you going to want to evaluate. So let's get into it. So we have, for the first one, rad 4 minus y squared, and I'm integrating with respect to y. So maybe you'll recall, if you have square root of a constant minus y squared here, it's trig sub time. I'm so very sorry. So you go, well, it's doable, but perhaps the other order would be better. And I'm looking at it and I'm going, oh yes, of course it is, because there's no x. So if I integrate with respect to x, I'm just going to add an x in there. Then I'm going to have a 2y, and then I'm going to do an easy breezy u sub. So if you're deciding which one to go with, it's this one. All right. And if you can imagine a few steps ahead, then you're going to be in really good shape. Anyways, it comes out to 16/3. If you need to just do some computation when you wind down in the evening, you can verify that. All right, moving on. Let's look at this next example here. We have the double integral from 0 to 1, square root of y to 1. Okay, and then we have square root of x cubed plus 1 dx dy. And you might be thinking, oh my goodness, this is too easy. They already set the whole thing up for us. What are they thinking? And you're ready to dive in and start integrating, but wait. How do you integrate the square root of x cubed plus 1? Well, you've gone through calculus too. Surely you feel like you know everything there is about integrating, but I'm so sorry, we can't do it. No. So what happens? You're actually going to draw what this base region is and see if perhaps you can switch the order to give you an integral you can actually manage. Yep. All right, so we have 0 to 1 on the outside, and those are limits for y. And then we have rad y to 1, and those are limits for x. So that means the region is bounded by x equals rad y and x equals 1. So x equals rad y, that's the same as y equals x squared, right? We know y equals x squared. That's our good friend, the parabola. Okay, and then we're only going to graph the portion that's bounded between 0 and 1 in the y direction as well. So here's x, here's y, 1, 1. I'm liking it better already since I'm thinking of it as y equals x squared. And then now, here's the region D. So let's switch it up. Let's put the constant limits for x on the outside and then the limits for y on the inside. So outside would be 0 to 1. Inside, I'm going to do the region bounded on the top by x squared. So that's my upper limit. Lower limit's going to be 0, right? This is y equals 0. And then now I have square root of x cubed plus 1. All right, cool. And then now it's dy dx. Ooh, are we happier? Absolutely. Because notice I'm integrating with respect to y first. There's no y's present here. So that means that's just all a constant. So if I'm going to anti-differentiate, you're just going to add a y in there. So keep this 0 to 1 on the outside. Now I'm going to have y times the square root of x cubed plus 1 evaluated from 0 to x squared. And then you still have that dx. Now be careful, careful. These get plugged in just for y, right? We're treating x as constant still. So I have 0 to 1 x squared times the square root of x cubed plus 1 minus 0 dx. Love it. And then this is going to make the most beautiful u sub, because you would let u equal x cubed plus 1. Du would be a 3x squared dx, yada, yada, yada. Okay, and then you should end up with 2/9 times 2 rad 2 minus 1. Okay, very good. Now, we're going to look at some properties of double integrals to finish up, and many of them are super similar to the properties of single integrals. It extends rather naturally. So if you're integrating over some general region, then you can distribute your integral over the sum of two functions. You can also pull a constant outside. These are pretty much the same when we did rectangular regions as well. And then if you have f of xy always greater than or equal to g of xy, then it's double integral over d is going to be greater than or equal to double integral of g of xy over d. And then also, if you could write the region D as the union of two other regions that don't overlap, right, except perhaps on the boundary, then you can split the integral up. And we actually did that in the example with that triangle, where we had to split it up into two integrals in the x direction. And then if you evaluate a double integral of 1 times dA, instead of giving you a volume, it gives you an area. Or you could think of it that that's a very special solid where the volume is equal to the area because the height is 1, right? So cool. And then if you have some function bounded by lowercase m and uppercase m, then you can bound the value of its double integral over d by little m, lowercase m times the area of d, and capital M times the area of d. And we are actually going to use that last property for the following example. So use property 6 to bound the double integral over d of e to the x squared plus y squared dA on the disk with center 0, 0 and radius 1/2. So this is d, right? D is a disk centered at 0, 0, radius was 1/2. So the area of this disk, it's a circle, so it's pi r squared. So pi times 1/2 squared, so it's pi over 4. And in order to bound this integral, I first have to just bound the function. I have to bound f of xy. And what's popping out at me is this x squared plus y squared, right? Since we're integrating, or this function e to the x squared plus y squared lives only over this disk, I know x squared plus y squared has to be less than or equal to 1/4 and greater than or equal to 0. Yes, it lives on the circle or disk centered at 0, 0 with radius 1/2. Okay, and then e is strictly increasing, so I can take e raised to each of the values in this bounded inequality, and everything will be preserved. So e to the 0 is going to be less than or equal to e to the x squared plus y squared, which is less than or equal to e to the 1/4. So now I have my lowercase m and my capital M, right? Bounding my function f of xy. Okay, so I'm going to multiply each of these by the area of d, which is pi fourths. I know e to the 0 is 1. So 1 times pi over 4 is going to be less than or equal to the double integral over the region D of e to the x squared plus y squared dA, which is going to be less than or equal to e to the 1/4 times pi over 4. And that's all they wanted us to do, was just bound the integral. We can't evaluate it just yet. I'm so sorry. You're going to have to stay tuned for the next video to see how on earth we would evaluate that double integral. So this concludes the lesson.